Previously, we have discussed Boyle's law and Charles' law. Boyle's law is a relation between pressure and volume. Charles' law is a relation between volume and temperature. Now we want to derive a general gas law, a relation between three variables, that is pressure, volume and temperature. Initially, we consider a gas having volume V1, pressure P1 at temperature T1. This is the diagram. The first container, the small container, shows a gas having pressure P1, volume V1 and temperature T1. This gas is transferred into another container, so volume becomes Vx. Initially it is V1, it changes from V1 to Vx, pressure changes from P1 to P2, but the temperature is kept constant. In this transformation of a gas from first container to the second container, the temperature of the gas remains constant. It is T1 initially, it is T1 finally. The pressure changes from P1 to P2 and the volume changes from V1 to Vx. Because temperature is kept constant, so we can apply Boyle's law. Initially P1 V1 equals P2 Vx. For first container P1 V1, for second container it is P2 into Vx. From this relation we can derive the value of Vx. Vx equals P1 V1 upon P2 after rearranging the variables. This is equation number 2. Now this container, which is a final container here, is an initial container. T1 temperature, P2 pressure and Vx volume. Now this gas is transferred into another container but at constant pressure. The pressure P2 here, temperature changes from T1 to T2 and volume changes from Vx to V2. The gas is transferred into another container at constant pressure P2. It is same here in both cases, while volume and absolute temperature of a gas becomes V2 and T2 respectively. Initially the temperature is T1, it changes to T2 and volume changes from Vx to V2. Because pressure is constant, so we can apply Charles' law. Initially Vx upon T1, finally V2 upon T2. Rearranging this relation, we can derive an equation for Vx, and this is equation number 2. The left hand side of equation 1 and equation number 2 contains Vx, so we can compare equation 1 and 2. P1 V1 upon P2, it equals V2 T1 upon T2. After rearranging further, P1 V1 upon T1 equals P2 V2 upon T2. We can further relate it as P2 as P3 V3 upon T3, P4 V4 upon T4 and so on. So it is important to note that the ratio between pressure, volume and temperature for first stage, for second stage or third stage remains constant, it remains same. So simply we can write PV upon T equals constant. This relation is written for 1 mole of a gas. Simply, the value of constant for any gas having 1 mole is found to be a constant and it equals 8.31 joule per mole Kelvin. So simply I can write constant as a capital R. It is a capital R means it is a universal gas constant independent of the nature of gas. I can write it for any kind of gas. Now I want to make it more general for n moles of a gas. For n moles of a gas I can write it small n, which represents number of moles, either 2 moles, 3 moles or so on. This T goes here to multiply. So PV equals nRT. This is a more general equation of state. For any kind of state having any pressure, volume and temperature, I can use it. P here is a pressure, V is a volume, N is number of moles, R is universal gas constant and T is the temperature of the gas. Okay, this is the more general relation and I can use it in numerical calculations to find any one variable which is required. Okay.